A large number of visual-inertial SLAM systems have been proposed in the last decade. Many of them demonstrate high accuracy and robustness in indoor and urban environments. However, when it comes to the agricultural environment, they present problems in correctly estimating the pose of the robot. Among others, agricultural environments are challenging for visual navigation due to insufficient and repetitive texture and direct sunlight. Adding inertial measurements provides a slight improvement in the estimation. Nevertheless, state-of-the-art visual-inertial systems accumulate significant errors after navigating a few minutes on arable lands. In this work, we present a GNSS-stereo-inertial SLAM implementation that fuses GNSS visual and inertial measurements using a tightly coupled approach. We evaluate our implementation on agricultural environments using real-world data. In addition, we release our implementation in order to facilitate its usage, extensions, comparisons, and evaluations by the robotics community. We present a system built upon the Advanced Visual Inertial System, or SLAM 3. To enhance its capabilities further, we've integrated a GNSS factor into the nodes within the window keyframe of the local bundle adjustment. By integrating GNSS data into our SLAM 3, our system can leverage the strengths of both GNSS and the visual inertial system. To achieve our objective, we must first define a residual for the GNSS factor. This involves comparing the translation of the GNSS antenna as determined by our SLAM 3 with the translation provided by the GNSS measurements. The translation calculated by our SLAM 3 is expressed in the W frame based on the robot's pose at times t0 and ty, along with the extrinsic translation between the IMU and the GNSS antenna. On the other hand, the GNSS measurements provide the translation in a coordinate frame known as A0, established by the first GNSS measurement that arrives to the system. To deal with both coordinate systems, we need the rotation between A0 and W. During an initialization process, we can obtain this rotation by using GNSS measurements and the robot's position established by our SLAM 3. By applying the Umeyama aligning method, we calculate the resulting rotation, which remains fixed throughout the entire optimization process. We evaluate our system on the Rosario dataset, which comprises sensor data collected by our weed removal robot in arable lands. To ensure comprehensive testing, we corrupt the GNSS RTK measurements with additive Gaussian noise, simulating conventional GNSS measurements. Furthermore, we took our robot to the field and recorded 3 new sequences in a soybean field. During these sequences, we incorporated GNSS measurements from a conventional GNSS receiver without RTK capabilities. This allowed us to assess the performance of our system in real-world conditions where RTK enhancements are not available. Through these evaluations, we gained valuable insights into the robustness and reliability of our navigation system, further validating its effectiveness in various agricultural environments. In our evaluation, we directly compare our system to 2 state-of-the-art systems, visual-inertial SLAM 3 and a loosely coupled fusion system called Beans Fusion. The results clearly demonstrate that our system surpasses the performance of both systems. To conclude, we can see our framework in action. On the left side, you can observe the estimated keyframe poses represented in blue, alongside the noisy GNSS measurements depicted in red and the map points in green. On the right side, incoming frames and tracked features are presented.